This video is going to talk about vapor pressure in solutions and how it's related to the boiling point of that solution and the freezing point of that solution. So when a liquid is at a certain temperature, there's always some vapor above it. And generally, the higher the temperature, the higher the amount of vapor is. So for example, in winter, air is pretty dry before it reaches 100% humidity, whereas in summer, air at 100 degrees Fahrenheit can actually hold quite a bit of water, and so it can be extremely humid, but still hold even more water until it reaches 100% humidity. So one thing that does affect the vapor pressure of a solution is how much stuff is dissolved in it. So the more stuff you have dissolved in there, then the lower the vapor pressure is going to be. So for example, if you look at the amount of vapor in equilibrium above a salt solution, it's actually going to be less than a amount of water vapor above a pure water container. Okay, as a consequence of this, since the boiling point is the temperature at which the vapor pressure of your solution reaches atmospheric pressure, well, for solutions, they already have a lower temperature, so you actually have to raise them, lower vapor pressure, so you have to raise them to a higher temperature to get them to boil. And the same thing happens with a freezing point. The more stuff you have in solution, then the lower the freezing point is going to be. The equation that you use for both boiling point and freezing point is pretty much the same. You just use a different proportionality constant. It turns out it's proportional. If you double the concentration of stuff in solution, then you double the change in the boiling point and the change in the freezing point, which are different numbers. Okay, so water's normal boiling point, of course, is 100 degrees C. And so whatever you calculate for the change in the boiling point, you add to 100. The normal freezing point of water is 0 degrees C. So whatever the change in the freezing point is going to be, you subtract from 0 degrees C. Okay, so we're just going to do a simple problem. Let's say we have 0.5 mole of calcium chloride in a kilogram of water. Okay, all of these calculations are going to be per kilogram of water. Okay, well, first thing you note is that 1 mole of calcium chloride is actually dissolving as 3 particles. The particles being the calcium 2+ ion and a chloride ion and another chloride ion. So this it's very important for you to understand how many ions are going to be dissolved in a strong electrolyte, because that's what's going to determine your moles of particles. And then the proportionality constant, which of course is not anything you need to memorize. You'd always be given this. But if you have a kilogram of water, it turns out that the temperature change is 1.86 degrees C per mole of particles. And so the change in the freezing point, now this is for freezing point. This is the number used for freezing point. For boiling point, you use a different number, and it happens to be this number. So we're actually going to calculate the temperature at which this thing boils and freezes. Okay, and so the freezing point is going to, the change in the freezing point, so this is the change in the freezing point, delta T F. It's going to be 2.79 degrees C. And so up here, instead of 0 C, it's going to be minus 2.79 degrees C. All right, and so what is the boiling point going to be? Well, instead of 1.86, we can have 0.51, and I'm going to have to. So what about the boiling point? Instead of 1.86, we use 0.51, so I need to calculate that. 0.5 times 3 times 0.51. So the change in the boiling point is going to be 0.765. And so the so I'm just going to round it to the nearest tenth of a C. It's going to be 100.8 degrees C.